interned here at INRIA in the medical imaging team Epion, and was part of the ERC project on geometric statistics. And the problems I was faced with at the beginning of my thesis was to analyze the cardiac function of this shape of right ventricles. So the right ventricle is the part of the heart that sends blood to the lungs in order to fill with oxygen, and has a large capacity to reshape or remodel in the presence of shape or volume overload, which are caused by some diseases. So for instance, here we had pulmonary hypertension, which is a disease that occurs because of an increased pressure in the pulmonary arteria, and that can cause swelling and scarification of the ventricle. And we had also atrial septal defect and tetralogy of Fallot, which are two congenital heart diseases. In both cases, there's a circulation of blood between the two chambers of the heart, resulting in an increased pressure and also sometimes volume overload. And as you can see, the volume of the shape increases a lot compared to that of the control group. And so the challenge is really to characterize the impact of the disease on the cardiac function, which involves comparing deformations of different anatomies, thus raising the need for a normalization strategy. And this work was done in a greater context of increased acquisition of medical data in health, from molecular data called omics to imaging data acquired by MRIs, scanners, echographies, to text data from electronic health records. And there is a strong incentive to leverage this routine clinical data, with both the aim first to improve patient care by performing, for example, early and automated diagnosis, or in the long term to reach precision medicine, or, and this is more our case, with the hope to acquire new medical knowledge by performing a finer stratification of disease subtypes, or by identifying new risk factors, new biomarkers of the disease, or by being able to detect earlier the disease onset and better analyze its evolution. In this context, machine learning methods, and in particular deep learning methods, have shown great performances, and especially for tasks such as segmentation or pattern detection, for example, with the famous UNet architecture or RCNNs. So they are good at performing segmentation or detecting brain tumors, classifying skin cancers, and so on. Basically, they are good at analyzing texture, but this is at the detriment of analyzing higher level information such as anatomical shape or deformation. Moreover, they are challenged by the heterogeneity in the data and the small number of samples. We thus resort to methods from the shape analysis or computational anatomy literature that use smooth deformations in order to quantify the difference between shapes. And as both shapes and smooth deformations are nonlinear, this raises the more general questions of performing statistics on nonlinear spaces, and in particular on manifolds. And so this occurs for analyzing deformations of right ventricles. This could also occur to analyze evolutions of the brain acquired from MRI, or to characterize brain connections when represented by their covariance matrices of some signal from fMRI or EEGs. But also even in greater fields to characterize protein structures. So each amino acid residue can be characterized by two angles, yielding a data set on the two torus, which is nonlinear, or locations on Earth lie on the sphere, which is also nonlinear. So all these examples are examples of data that lie on a manifold, and for which we need to perform statistics and machine learning. And this field can be called geometric statistics, encompasses the generalization of statistics and learning methods to manifolds. And this process is necessary first for mathematical coherence. If you think of the mean on the sphere, of 2 points on the sphere, it won't lie on the sphere. And so it goes for interpolation scheme. It is also necessary for statistical consistency. If one wants to sample from a uniform distribution on the sphere, it is different from sampling parameters in intervals from a uniform distribution and mapping them through spherical coordinates. There's also a modification of the central limit theorem in the presence of curvature that modifies the statistical testing procedures. And finally, geometry can be thought of as a prior that is useful to cope with the lack of data and consequently improve learning with less data. And in all these tasks in geometric statistics, I was challenged by a common need to transport tangent vectors. So this can be to transfer deformations from one anatomy to another, or to transport gradients when performing optimization on the manifold, or to perform domain adaptation or transfer learning, for example, with those EEG recordings, where one wants to learn a model around an area of the manifold and transport it to another area, or conversely, move some data around one mean to another one. And for all these challenges, we can use a tool called parallel transport, defined from Riemannian geometry. And this idea will lead most of the developments of this thesis. So I will first delve into the field of geometric statistics and go and show how we can go from theory to an efficient implementation with a framework called geomstats. Then I will focus on the computation of parallel transport with approximation schemes called ladder methods. I will show that they converge and give their speed of convergence. And finally, I will apply those results to the normalization of cardiac deformations. So first, geometric statistics with geomstats. So geomstats is a Python, open source Python package for computations on and statistics on nonlinear spaces. It was started by Nina Mulan 2 years ago, and I joined the project and contributed to a large extent. And the goal is to develop and provide the tools to perform learning on manifolds. But why was it needed? As you can see, there are other packages that deal with data on manifolds, but they all either deal with one application, such as optimization or deep learning, or with one manifold, such as SPD matrices or 3D rotations. And as a researcher in geometric statistics, one wants to apply our theorem and test them on different manifolds with the same computational tools. So there was really a need to go beyond application-specific implementations, while of course matching the existing ones when they exist. For example, our implementation of SPD matrices matches the performance of that of Nylern and Riemann that are dedicated packages from the neuroscience community. And so this involves identifying what can be generic and reused in our code in order to make it more modular, so that different structures can be combined together, and so that we can choose the most efficient formulation when it is available, and when it is not, that we can leverage numerical tools such as automatic differentiation or optimization. And this really opens the door to new metrics and new algorithms for which we don't have a closed form solution, and for which it was not possible to compute before. More precisely, geomstats is first composed of a geometry module that deals with data on Riemannian manifold. So recall that a manifold is a space that is only locally diffeomorphic to RP. It can be described either by a set of charts around each point. So UX would be a neighborhood around X, and phi is a map that verifies certain regularity conditions and maps the manifold to the neighborhood in RP. But alternatively, it may be it can be seen as embedded in a larger vector space and defined by a local immersion or submersion, which are two ways basically of visualizing objects in space. And the immersion, we can think of it as a coordinate system that indicates how a grid in RP, a regular neighborhood, must be deformed to parameterize the manifold. And the submersion can be thought of as encoding constraints, where the manifold is defined as a set of values that verify, for which the constraint is verified. This is the case of both circles here that correspond to one value of the radius. And this is why manifolds are so ubiquitous in applications, as soon as we have data under some constraints. And another tool that we need to perform geometric statistics is the Riemannian metric, which is user-defined and is an additional structure. It is a smooth assignment of inner products on each tangent spaces. So it allows to compare tangent vectors within one tangent space of the manifold. And more globally on the manifold, it defines a certain class of curves called geodesics that minimize the length between 2 points, or alternatively, the energy between the 2 points, and define a distance function that measures the length of those geodesics. And the Riemannian metric is also associated with a unique notion of parallelism called the connection that allows to basically differentiate tangent vector fields so that it allows to compare them in small neighborhoods of the manifold. And more globally on the whole manifold, it defines parallel transport, which I will define more precisely. And as the metric must be chosen by the user, it is important to be able to test different metrics. So it's important to be able to combine the structures. And in order to do so, we chose to use object-oriented programming, meaning that all the structures in geomstats are implemented in classes. And to structure these, we use abstract-based classes, ABCs. So an ABC is a class that contains abstract methods. A method is abstract if it is declared but does not contain any implementation. So it may not be instantiated, but the abstract methods will be implemented by the subclasses of the ABC. And so we use ABCs in geomstats as the skeleton of the geometric structures. It allows to constrain the class to have what is expected from the structure. So for example, the level set class defines manifolds that are embedded in a vector space by a submersion. So it takes as input the embedding space, the submersion, and its derivative. And this allows to define the belongs method that evaluates if a point belongs to the manifold by simply evaluating the submersion at that point. And it allows to check whether a vector is tangent at that point by evaluating the tangent submersion at that point. However, the projection method must be implemented in a case-by-case situation, so it is left as an abstract method and it will be implemented by the subclasses. So we implement a number of level sets, class in geomstats, for example, the hyposphere, in which case the submersion is a squared norm, and it is used in applications to model geographic data or orientations. We also have other ABCs for vector spaces. They are basically the embedding spaces. And we have open sets that corresponds to the case where the manifold is defined by an immersion, where the immersion is the inclusion map. So it is for the case where the dimension of the manifold is the same as that of the ambient space. This is the case of the space of symmetric positive definite matrices that are used in applications to model covariance matrices of signals, for example, of brain connections. But manifolds are mainly useful to model more abstract and higher level properties, and in particular to model invariance properties. For example, in finite dimension, the space of Kendall shapes is defined as what remains when we remove from a configuration of landmarks the effect of translation, rotation, and scaling. And this process of removing those effects involves identifying the shapes that differ by one of those transformations. And this process is called taking the quotient by the corresponding group. And we retrieve a manifold on which a metric is defined that directly encodes those invariance properties. This generalizes to infinite dimension with the space of curves, in which we further want to encode the invariance by reparametrization. So in order to implement those in geomstats, we implemented more abstract base classes for different structures, for example, for Lie groups and their Lie algebras. This allows to define the fiber bundle structures that is used to define a quotient metric. This is the case of shape space and the space of correlation matrices and of the closed discrete curves. And then we have a common interface for hyperbolic geometry. And we can combine existing manifolds by taking products of existing ones. Okay, so now that we know about the geometry module, we can use it to perform statistics and machine learning. So the statistical learning module of geomstats is designed to match the scikit-learn API so that little knowledge of geometry is needed, and it is compatible with deep learning tools to compute efficiently. So the fundamental example of geometric statistics is the Fréchet mean. It is defined as a point that minimizes the sum of squared distances to the data set. And as there are no closed form solutions, it must be solved by computed by an optimization problem, a gradient descent. So it is implemented in an estimator called Fréchet mean that takes as input the geometry, here's the metric. And so it is compatible with all the metrics of geomstat because they all have the same structure. And then the fit method can be called on some data to return an estimate of the mean. Other examples are the geodesic regression that generalizes linear regression by looking for the geodesics that best approximates a data set. So we are given time points ti on the real line and target points xi on the manifold. And we are looking for the geodesic that best approximates the data so that it minimizes the sum of squared distances between the target points and the points on that geodesic at times ti. Again, there are no closed-form solutions, so this is solved using an optimization technique, and this is implemented in an estimator that takes as input the space, and the fit method can be called. A last example is that of principal geodesic analysis that generalizes principal component analysis. In this case, we are not given the TI's variables, so we use a projection on the geodesic by minimizing the square distance. And then we minimize the sum of residual errors, which is here the sum of both green distances. And in this case, note that we did not implement Jacobi fields to compute gradients, but we use automatic differentiation throughout the whole procedure. So even though this is only a proof of concept on the hypersphere, we hope to generalize it to other manifolds. So to summarize on this part, my contributions were to implement new geometries and learning algorithms within the geomstat framework, with a particular focus on numerical schemes for parallel transport and geodesics in the cases where we don't have a closed-form solution, and also a focus on the architecture of the geometry module in order to make it more structured and more coherent with the mathematical theory. This work led to theoretical developments. For example, I derived a reduced parallel transport equation on Lie group with a left invariant metric. And it led to collaborations. For example, with Emmanuel Chevalier, I performed tests for his bi-invariant statistical model on the group of rigid body transformations. So we can now focus on the computation of parallel transport with ladder methods. So there are a class of approximation schemes called ladder methods. More formally, parallel transport is defined by a differential equation, namely x is parallel along a curve gamma, if and only if nabla, this is a connection, gamma dot x equals 0. So nabla measures the rate of change of the connection with respect in the direction of gamma dot, which is the velocity of the curve. So this means that x must not vary when compared to the velocity of the curve and when going along the curve. So this defines a differential equation which ensures the existence and uniqueness of a solution. So it defines a map between tangent spaces of the manifold that is linear and isometric in particular. However, as it is a differential equation, it is not straightforward to solve. So parallel transport is not necessarily easy to compute. And a certain class of approximation algorithms have been proposed. And I will focus on ladder methods, so the Shields ladder and the Topol ladder, that consist in building geodesic parallelograms, small geodesic parallelograms to approximate parallel transport. So Shields ladder works as follows. If we want to transport a vector v along a geodesic with initial velocity w, we will use the midpoint rule to construct parallelograms. So we first divide the main geodesic in a number n of small segments, here 5. And then for each segment, we construct a parallelogram by first computing the geodesic between xv and x1, finding its midpoint, computing the velocity that leads from x to that point, extending that geodesic by the same amount. And in a Euclidean space, we would retrieve a parallelogram. So here, doing this in a small enough neighborhood, we hope that UW is an approximation of the parallel transport of V along W. And then this construction can be iterated along the main curve until we reach the point where we want to transport the vector. So this algorithm is called Shields ladder. It was introduced in the 70s by Alfred Shields in the context of physics and gravitation. So there were no proof. And the first proof that concerned only one parallelogram, so showing that one parallelogram is indeed an approximation of parallel transport, was done by Kefetz et al. In 2000. And then Marco Lorenzi and Xavier Pennec adapted this scheme and introduced the pole ladder, which uses the geodesic along which we transport as diagonal of the parallelograms. And this allows to compute less geodesics because the intermediate one here is not necessary. So it is cheaper. And they show that it is also a first order approximation of parallel transport and even a third order approximation. However, there were no results in the literature for the iterated schemes and for the case where the geodesics were not known exactly, but only approximated. So my first contribution to this field was to characterize the defect of parallelism in parallelograms and by generalizing the midpoint rule. Namely, by using Taylor approximations of the exponential and logarithm maps, we can compute an approximation of the vector A that maps to the midpoint between xv and xw. And it is indeed the middle between v and w. But there is a correction term that is due to the curvature tensor, which is well known in Riemannian geometry and quantifies the deviation of geodesics from straight lines. And by the big O of 4, I mean that all the terms in the remainder involve curvature and its derivative, and V or W appear at least 4 times in them. So if V and W are small, those terms are smaller than the third order term here that involves curvature. And by propagating this approximation of A, we can prove, we can compute an approximation of U, the vector obtained by the Schilf-Zeider construction, and compare it to UW, the true parallel transport of V along W. And we obtain something that is directly proportional to curvature. And as you can see, it is bilinear in V, linear in W, and it is symmetric in V, and it is of order 3. And then this allows to define a sequence for the iterated scheme and to prove that it converged. So we define a sequence initialized at V. Then recall that we have scaled W to compute only small parallelograms. We must scale also V so that they are the same order of magnitude, but we have the freedom to scale it by a larger amount. So we introduced an exponent alpha that is defined by the user and that can be chosen. And then by propagating the Taylor approximation of one parallelogram and summing them up, we prove that the overall error made after n steps goes to 0. So we are indeed computing an approximation of parallel transport, and it goes to 0 with speed that is bounded above by 2 terms, one that depends on alpha, and the second that is quadratic. And the 2 constants tau and beta depend on curvature and on its derivatives. And we verify those results on simulations. So on the left, on the hypersphere, with simulated vectors that we parallel transport. And different colors show different values of alpha. As you can see, it is linear when alpha equals to 1 and quadratic when alpha equals to 2. And in between, we can reach any value of alpha. And the optimal value is 2 because we have the beta term before. And then we verify that the constants depend on curvature by using a simulation on the space of SPD matrices, in which case the curvature is negative. And this explains why the errors here are negative, but they also go to 0. Then we apply the same methodology to analyze the pole ladder and show that it also converges to 0 when n goes to infinity. But in this case, as one parallelogram is a third order approximation, there is no third order term. And so we don't need an exponent alpha. And the result is invariant to any choice of alpha, meaning that the convergence is quadratic in every case. And to probe the dependence of gamma on the curvature, we performed experiments on the Lie groups SE3 of rigid body movements in space using an anisotropic metric defined as such. So G-rot is the usual metric on rotations, and beta is an anisotropy parameter on one axis of the translation. And as you can see, with different values of beta, showing different colors here, we modulate the speed of convergence, but it is always quadratic. And there is a particular case when beta equals to 1. In this case, indeed, the metric is in fact isotropic, so the space is symmetric. And actually, we can prove from first principles that pole ladder is exact in symmetric space. On this topic, I also showed other results, namely that these convergence results remain valid when geodesics are only approximated by a numerical scheme. So in this case, if we cannot compute the geodesics exactly, but we replace each exponential map by an approximation scheme such as a Runkuta step of a sufficiently high order, and the log, we approximated them by inverting the step, Then I showed that if the order of the scheme is sufficient, the points that we obtain stay close enough to the true construction of pole ladder, so that the approximated sequence converges to the true sequence, and so that the vector converges to the true parallel transport. And this really opens the field of applications to widely, because it applies when we cannot compute geodesics in closed form, for example, in computational anatomy. And I also studied the fanning scheme with the same tools. So the fanning scheme is another approximation method introduced by Maxime Lou in particular, and Stanley Derleman. And it uses Jacobi fields to compute parallel transport, but in theory. But in practice, its implementation is very close to that of the Shields ladder, with the difference that a vector W plus epsilon V is used instead of the vector A from the midpoint rule, so that it introduces another third order term that cannot be reduced by using a scaling with alpha, because it is not bilinear in V. So we showed that this scheme cannot be improved with the same trick as the Shields ladder was. So to summarize both contributions on ladder methods, I contributed to a better understanding of Shields ladder, and by showing that it converges and that it couldn't be improved to reach a quadratic speed. Then I showed that pole ladder was naturally quadratic and less costly, and that both schemes work with approximate geodesics. And then I made the link with existing literature, in particular with the fanning scheme. All these results were published in Foundations of Computational Mathematics. So now that we can compute on general manifolds and compute parallel transport with ladder methods efficiently, we can apply those results to our initial problem of normalizing cardiac deformations. And in order to do so, we should use parallel transport to transfer deformations from a subject's anatomy to an atlas. And of course, this problem of normalizing cardiac deformations is not new in itself, and it was addressed partially in the literature before. Methods such as reorientation or conjugation have been proposed in the framework of free-form deformations. But in many cases, they made the assumption that the deformations that were being transported were small deformations, and they transported along deformations that were also small in some cases. Then parallel transport was proposed to normalize deformations. It was first computed with Jacobi fields by integration or by the fanning scheme, in both cases within the LDDMM framework. And ladder methods were proposed also to normalize deformations, and they were computed in the stationary velocity field framework. In this case, it is easier to compute deformations using the BCH approximation. And so logarithm can be approximated. So this scheme is more easily, ladder methods are more easily applicable with stationary velocity field. So in this work, we use ladder methods in the LDDMM framework, thanks to our results from the previous section. And we applied those in a context where the deformations were very large, with large volume changes, both in the temporal dimension for within a patient, and for interpatient registration. So more precisely, by deformation, I mean a diffeomorphism. So it is a deformation of space that is smooth and invertible, and whose inverse is also smooth. And using diffeomorphisms is useful to encode the constraints of how an anatomical shape must deform without sharing or tearing, but in a coherent way. And following the work of Miller, Trouvé, and Younes, and others, we use diffeomorphisms that are obtained as flows from the identity. So here phi is a diffeomorphism that we're looking for, and it is obtained by integrating a velocity field B that is defined in the ambient space. And more precisely, we used velocity fields that are parametrized by a convolution of momentum vectors and control points, and using a Gaussian kernel. This space of vector fields forms a reproducing kernel Hilbert space, which is identified with the tangent space of the subgroup of diffeomorphisms of the ambient space. And in turn, it induces a right invariant metric on the subgroup of diffeomorphisms, meaning that the norm of a deformation, its amplitude, can be measured by integrating its velocity field in time. And results show that the flow of a velocity field is geodesic if and only if the control points and the momentum vectors are solutions to this Hamiltonian system of equations, meaning that given initial conditions, we can integrate those flow equations to compute the velocity field and integrate the flow equation to compute a deformation. And then by applying the deformation to a shape, we can parameterize the path, parameterize the deformation of an anatomical shape. And in fact, the metric on the space of diffeomorphisms, by using this action on the space of shapes, the metric projects and it turns the space of shapes as a Riemannian manifold, so that we can measure distances between shapes by measuring the length of the diffeomorphisms above. And this involves solving a registration problem, which aims at finding the best initial conditions of a diffeomorphism to match a source shape on a target shape. So there is a data attachment term in the criterion and a regularization term that penalizes large deformations. And for the data attachment term, many have been proposed in the literature. We could have used currents that consider shapes as oriented measures, or varifolds that work with non-oriented shapes on normal cycles. But as we have a very clean data set with point-to-point correspondences, we use the L2 metric. So here are two examples computed with the software Deformatica. On the left, it is a deformation between a circle and an ellipse, with the continuum of colors showing the whole trajectory between the two shapes. And on the right, it is a deformation of the right ventricle from the end diastolic frame, when the heart is the most dilated, to the end systolic frame when it is contracted. In red, the end systolic frame, and in blue, the end diastolic one. So green points are the control points, and the blue arrows are the momentum vectors. As you can see, they're a bit noisy, but once convolved by the gradient, they are more coherent, and they can be used as descriptors of the deformation of that patient during the contraction. But these parameters that encode the deformation are specific to the initial anatomy of the subject, so we must normalize them in order to compare them across populations. And in order to do so, we use the following framework. So for each subject, we define the reference time to be the end diastolic time. We compute an atlas at end diastole from the control group. So again, there is a full literature on how to compute atlases, but we may just think of them as a Fréchet of the shapes of the control group. And so for each patient, we perform a registration to encode the time deformation, the corresponding time deformation in the frame of the subject. And then all these time deformations are transported by parallel transport to the atlas in order to reconstruct a sequence that is a deformation of the atlas, but is personalized to each patient, so that we can then consistently compare them. And every time we use parallel transport, we used our new implementation of the pole ladder within the Deformatica software, and that is more stable than the existing one because of the properties that we highlighted in the previous section. But beyond numerical stability, we in fact encounter a problem that was due to the large volume changes that occur between the patients at the reference time. So for example, here, this is an example of patient with a very large ventricle at the reference time at end diastole. It is much larger than that of the atlas. And because the parallel transport is isometric, the deformation that is a deformation of a large anatomy is transported to a smaller anatomy, and it is too big for the smaller anatomy. So this results in a non-realistic reconstruction that is too thin. So this is the blue one here. As you can see, it is very thin, and the curvature between the valves is very high. And at the apex also, it's really not realistic, so it cannot be used as a normalized frame. And moreover, this problem is linked to the initial volumes of the patients, which are themselves linked to the disease. And we can see this by looking at the distribution of ejection fraction errors. So the ejection fraction is the relative volume change between through the deformation. And by measuring the one that occurs on the original patients and the one on the normalized patients, we measured the error. And as you can see, it is related to the disease group. So this is problematic for a normalization strategy. And in fact, this problem was already reported in 2D. It is more of a scale problem. It occurs when, we can see it, when we transport the evolution between a circle and an ellipse from along the deformation between a large circle and a smaller circle. So on the right, we retrieve a smaller ellipse, but its anisotropy is much increased. And this was reported before by the work of Nittamer and Bialar. And they proposed to use a metric that decomposed between the volume changes and changes that preserve the volume, the scale. We propose another solution that is based on the scaling of the transported deformation. So we look for a factor lambda for each patient such that the ejection fraction is preserved after parallel transport. So for each time frame, we measure the ejection fraction of the corresponding time. We parallel transport the deformation, scale it by a factor lambda, reconstruct the shape, measure the ejection fraction, and we look for lambda such that these match. And lambda is looked for with a gradient descent. And it works fairly well. As you can see here on the right, with the same example as before, the shape is much more realistic, and it has the same ejection fraction, which is a simple and reliable indicator of cardiac function. So that these frames can be used in a later analysis. More quantitatively, we validate the scaling model by measuring the root mean squared error of the ejection fraction error. It is much reduced here. And we also measure the area strain error. So the area strain is the relative area change between each mesh, each triangle of the mesh during the time. As you can see, it is reduced, but not entirely, showing that the two factors, these two quantities are different and may not be normalized with the same method. And then we study the relationship between the scaling factor lambda and the volume ratios at the reference time. And in a log-log coordinate system, we find a very significant linear relationship that corresponds to this relationship here. And it is very significant with R2 equals not 92 and the slope around 2/3. So intrigued by this very significant relationship, we reproduced it in 2D. So with random deformations of a circle as template, and applying an affinity map that scales along one dimension for the temporal evolution, parallel transporting this evolution so that the ejection fractions match. And in fact, we retrieve the same relationship or a very similar one in a log-log space. So we may conjecture that the parameter alpha here is independent on the dimension. And finally, now that we have normalized the deformations, we can accomplish our initial goal of comparing them by performing statistics. And in order to do so, we first summarize each normalized sequence by a regression. So we look for one deformation such that the deformed template is closest to each sequence, each frame of the sequence. So this amounts to summing the data attachment terms through time during end diastole and end systole. And then we can perform statistics on these parameters because they are interpretable, localized, and low dimensional. They are parameters of a deformation of the atlas. And we can compare them by performing Hotelling tests. So here on the left figure, this is the mean parameters of the control group represented on the atlas. And on the right, these are the mean velocities for each group. and represented when they are significantly different from the control group in red. And as you can see, we find little difference for the ASD group, which corroborates with previous knowledge. And we find significant differences for the pulmonary hypertension and tetralogy of Fallot groups. But for the PhD group, they are more distributed across the whole shape, while for the TOF group, they are more concentrated around the tricuspid valve. So to summarize this chapter, we provided a more stable implementation of parallel transport with pole ladder and showed that parallel transport alone was not sufficient to normalize deformations in the presence of large volume differences. And we proposed a simple and effective scaling strategy to address this situation. This procedure was presented at ISB in Nice recently. And with this chapter, we can conclude this thesis. So I've contributed to the development of mathematical tools by studying ladder methods for parallel transport. I provided a better understanding of their performance and showed that their performance could be improved and that pole ladder should be preferred as it is cheaper. Then I contributed to the numerical tools to perform geometric statistics with geomstats. These tools are already useful for the researchers in the geometric statistics community, and we hope that they will be useful for the larger machine learning community. And this work led to theoretical developments and collaborations. And then I contributed to the applications to cardiology by studying normalization strategies for cardiac deformations. So I studied and evaluated different strategies based on parallel transport and proposed a scaling step to cope with large volume differences. For future work, we could use, so geomstats could go under major strong developments. For example, we could use explicit computations of curvature in second order optimization algorithm. This could greatly speed up their convergence speed and could have a great impact in optimization. Then now that we can compute parallel transport on any manifold, as soon as we have the geodesic or geodesic equation, we could use this parallel transport in order to do transfer learning on different manifolds. And this could also have a strong impact, as transfer learning is an important problematic in the learning community. And then we could deal with non-Riemannian spaces, for example, orbit space or stratified spaces that occur in many applications. For example, with pseudo positive semi-definite matrices, for which, so they occur in applications, but there is no adapted frameworks to deal with them. Then ladder methods could still be improved. For example, we could use more adequate integration schemes, depending on the geometry of the space, for example, on homogeneous spaces or on Lie groups. But the main challenge remains to bypass the computational cost of the log. And maybe this could be done by using a generalized midpoint rule that doesn't involve the separate computation of a log and an exponential, or by using a retraction of a sufficiently high order and its inverse. Finally, for the work on cardiac modeling, a better understanding of the relationship between the scaling parameter and the volume ratio remains to be done by, for example, reproducing these experiments with different data, different kernels, maybe different metrics, to see if we find the same relationship or not. And finally, maybe a finer study of temporal heterogeneity could lead into more insights into the dynamics of each disease. So I hope that these ideas will lead to an interesting discussion, and thank you for your attention.
Thank you. Presentation. So we just have a portion of this. We start with the regulars of the work, and we see the introduction of others. Thank you. Thank you for presenting for this presentation and for proposing me to use this
my script, which was very nice. So I enjoyed it a lot. And also the presentation. Yes. So I didn't expect to do just a little bit. Okay. So I think I will ask maybe a few questions just about geomstats and then. Basically, when you have your, I mean, what you presented, and which is very nice with the geomstats package, is that you can you have a very structured hierarchy of classes, and so it really reproduces the logic of mathematics. And then, so this is the main, as you explained in the presentation, with ABC classes. So these are abstract classes. The implementations are done in subclasses or direct classes. But finally, it looks like in the final step, what you have is just specific implementations for specific manifolds. And so my question is, how can we extend, for example, if we work with different manifolds and we want to use your package, how is it possible to add a wrapper so that we can so that's a question about implementation. So how would you like people to use your package? Like, just use what you've done, or maybe couple it with other packages?
Yeah, so the first step in geomstats was to implement the existing, the classic textbook Riemannian geometry, where we have all the closed form solutions. And this already covers a large, wide range of applications. And because I think that many people, when they use Riemannian geometry in signal processing, they will use the affine invariant matrix, or they will use one geometry that is the canonical one or the most famous one. So this is the first step of geomstats, to provide these tools so that it's easy for them to use. And then for more advanced tools and different metrics, this is the second step that we have initialized a bit later, well, now a year ago at least, where we used automatic differentiation and optimization to define different metrics. So we identified the minimal thing that must be defined by the user. For example, it may be the metric or the Christoffel symbols or Hamiltonian. And then we derive the tool downstream so that the geodesic equation may be computed, so the geodesics and so on. And so now there is, for example, a pullback metric, which is it's not in the manuscript, but it works as follows. So the user may only define the map that defines the pullback. And then with numerical methods, we can pull back the usual Euclidean metric from the ambient space with that geometry. And this is a longer term goal of geomstat, is to be able to define, to have metrics that are really tailored to each application with a few parameters or with a form that is defined by the user. And maybe in the long term, this could be, we could also optimize this metric. So for example, provide a metric defined by a family of maps by a pullback, and then optimize on the parameter of this family within a learning problem. And this could be a good, well, it could have a strong impact, but we're a bit far.
Okay, but just to follow on this question, so there's also what you explain here is that you will add more and more features, and so that it becomes more and more generic for the user. But I was also wondering if someone has already another toolbox for example, matching, for example, and he wants to use, for example, power transport, but he has not implemented. For example, in the third part, we explain that you use all letter methods for within the deformation graph, but it was not within the geomstats. So, would you like to be able to use both of them together, for example?
Yes, and I think it's the converse to what I said previously. It's if we have a downstream implementation, a lower level implementation of the geodesics and so on, we can embed it in the same API as geomstats by defining the Riemannian metric. By making a class that inherits from Riemannian metric, and it must only implement the abstract methods so that it works. And so if they are not implemented, it could use the generic machinery, but if they have been implemented in a different package, we could define the X method and map it to the other package. So this in this case, the geometry module of geomstat would more serve as an interface to the learning module. And I think it's not, maybe it's not user-friendly, but it's not a lot of work to make it work this way.
Yeah, another question still about geomstats so I think yeah, so we have a question about the case of infinite dimensional manifolds. For example, still in when we use a diffeomorphic registration for images, the framework, the magnet framework, infinite dimensional. But currently, geomstats is only for 5-dimensional.
Yes, well, there is the space of curves that approximates infinite dimension, and I think it is generalizable to landmark spaces at least. And for image spaces, we could do it, but maybe we would have to think of how to define the geometry by defining the cometric, for example, and then we would have the machinery to do the integration and to compute the flow, to define the exponential map and the higher level interface, so that it could use biotransport and the learning tools. And I think we could implement, for example, spaces of velocity fields. Maybe that only need to input the kernel or something like this.
But again, I was thinking that maybe it is better not to re-implement everything, but just offer the possibility to I mean, like these abstract classes, just to set up with abstract classes so that other toolbox can be plugged into your because
yeah. But I think as soon as the user has an exponential map and a logarithm map, then it can be plugged into a metric class, and which can be used in the learning algorithm. Thank you.
Okay, yeah, Nicholas, thank you again for a great presentation. Really tremendous amount of work. I'm really curious about the linear relationship in your scaling factor. If you go there, it's I mean, it's surprising. I mean, it is surprising that you get this kind of just like simply linearly scaling the transported vector, and that it stays linear across whole range of volume you got from orders of magnitude, right?
Yeah.
I mean, any intuition why this could at all?
So I'm not sure, but maybe it could be because I also implemented the metric described by the work of Vialar and Nitamer, in which they decompose really the volume change. So with a metric on R plus. and a scale invariant or a volume invariant metric. And so maybe the two could be theories could be related. Maybe this is an approximation of another metric. But if it's not, then and even if it was, in fact, this relationship is very surprising. I agree. But it's true that the first intuition is that it has to depend on the volume, right? Because so what we would have to prove is that there is a link between the norm of the diffeomorphism that is estimated to map to the atlas and the volume of the original shape that is being registered to the atlas. If we had a better understanding of this relationship, maybe we could understand more how it is involved here. Because the first impression was that the norm of the diffeomorphism to the atlas is too big because the volume was too big. So I will divide it by the volume, and it didn't work. So I divided by the square root and so on, and then I optimized the lambda. But I think the key would be the dependency between the norm of the diffeomorphism and the volume of the shape that's being transported.
Did you try in terms of the more classical language like this of normalizing the volumes of all the subjects? So literally just scaling them with a uniform scale so that they all have the same volume. Do you still
So this can be in the framework of the metric by Nittamer and Viala, because it involves first projecting all the shapes on the space of unit volume shapes, either by scaling them or by doing a gradient flow of their volume, following the volume map. So I tried those, but then I didn't try the regular metric, metric on the scaled deformations. I used the invariant metric because they were all of the same volume. So. But maybe this is something that Maxime Di Folco did, because I know that he used the normalization with similarities, not just rigid body registration, but also similarities. So this amounts to scaling them.
Right. And then do you need to still, I mean, then does the file transport work?
Yeah, it works.
Then you don't need to worry about it.
No, but then, yeah.
The other question I have is, we're talking about actual medical applications. I mean, when you're transporting, file transport is one transport. I mean, but is there any reason to believe that that's the right one to go? Because it's completely induced by the metric, which is given by a kernel, which is pulled out of a hat, and has nothing to do with the heart. So how can you think about, have you thought about linking that in a more interesting way, rather than purely as convenient?
Well, so as we have parameters for the metric and for here the scaling procedure, this could be learned from the data. So that to make it closer to the application. So defining criteria from the applications to choose the model. But yeah, it remains a convenient model that we have defined. But I think it's intrinsic to science. I mean, you have to define a model.
And last question about this scope again is did you try changing the variance of the kernel? You mentioned you showed it for different dimensions, but I didn't see anywhere the change in the sigma. Does that completely change the metric? Right?
Yeah. So I tried in the 2D experiment, and it's true that if the bandwidth of the kernel is not well chosen with respect to the frequency of the shape of the noise in the shape, then the parallel transport can become much harder to compute, in fact, and so the problem it's much more there's much more variability in the changes in the anisotropy that we observe.
But the linear relationship still remains. I mean, that's or do you lose that? Then is the linear relationship that the kernel is so big compared to the changes you see? That that's kind of
it remains because I mean in these examples I tried different frequencies of noise and different size, and I chose to plot one, but they appeared in several settings.
All right, thank you very much.
This one we go look at the insiders.
Yeah, so thank you for the presentation. I'd like to highlight that I'm curious that I'm not as mathematician as the others, and both the presentation and the manuscript I enjoyed very progressive way to introduce the concept with many examples. So I really liked reading it, even if some did very mathematical details I couldn't understand. Obviously, my questions will be a bit more on the cardiac part, and well, Sarah partially stole my question. I will complement it. Like, so if I understood correctly, the transport wouldn't be the same. It's not exactly the same line you follow. I mean, there's one geodesic, but if you follow a different path, your transport will be different, right?
Yes.
So you don't know that the heart exactly follows that geodesic. Actually, so would you think of clinical data that would be useful to try to see what is actually the path that a specific heart follows or a population heart follows, and would this help? Would it be very different result? Very different.
So, but there are two dimensions of the deformations that we estimate. There's the temporal deformation, which of course shouldn't be geodesic, and there's the subject to atlas deformation, which is the one along which we transport. And so there could be different answers, but a first intuition is that if the variability in the population is not that high, then because we're in a small neighborhood, it could be the path could be close to a geodesic. But then maybe something more interesting would be to, for example, to use data with follow-ups of the same patients to see, to have a better idea of how it varies, the inter-patient variability works. If we remain on the same trajectory, or if it's completely different, then we should rethink the model. And if we were to estimate, if we were to have a curve that is not geodesic between the ED frame and the atlas, then we can always approximate it by a finite number of geodesics and transport along each geodesic to apply the same framework.
Yeah, so this is very interesting for potential connection, better connection with the actual application. I have another very application related, which is like when we go from very simple computational models, the part like this here, that's the larger part. I mean, if you want to inject the same amount of blood, the large part does not require so much deformation. Okay, so in your experiments, when you think about the normalization you apply or not, is it partially what you see on your data or not?
I guess this is related because when we had a large heart and we transported that deformation to the atlas, it was much more deformed than what would be needed to have the same ejection fraction. So this work highlighted that there is also a problem with the norm of the deformation, and it's linked to the fact that if it's bigger, then it doesn't need to contract as much.
Yeah, so it's, we don't know really the answer whether we should preserve or not the contraction for that. And I was a bit curious, I have access to some computational models here at NLR. Why didn't you try that? Was it too much of we're looking to do some things on very controlled setup.
So you mean models with
Like cardiac, you have heart, you change the shape, you change the size, and then you have a trajectory, and you could perfectly apply normal parameter methods. There's less external factors.
yeah, it's true. It's more that I did not interact enough with the others of the team to do it, but it could be interesting to control a bit more of the factors. Yeah.
Now, a few more questions if I can. I was a bit curious. You're only processing a nice frequencies with times. I think we discussed that before. Why didn't you go for the full cycle, and what would be the challenges? Is it hard for you to consider that?
No, so it's we actually I tried it, and I used a spline model for the temporal deformation model. So with a second order term that allows to have a zero speed at some time when it starts contracting again or when it stops contracting. But then it was harder to analyze the results because there are much more parameters. And so that's why I restricted to the simpler model to understand the problem that we had here of the volume problem, of the volume changes. But the same framework does apply. And in fact, I did the normalization of the full sequences. I only did the statistical analysis of the systole.
Yes. And then the last question, like we know that this is a bit related to my first question. We know that there's a lot of external confounding factors. Some of them are the age, the condition of the patients, many other things. In which way would you handle this into your framework? Here you just shape changes. And would you handle them as confounding factors, as corrective factors? How would you approach this?
So maybe this could come in the this could come at different levels. So there is the time deformation, and so for example, here all the deformations are estimated for a time that between 0 and 1. So it amounts to normalizing the systole across patients. But maybe we could introduce a time warp that it would be estimated from other factors. And similarly, for the patient deformation atlas, we could think of, maybe we could use different actually trajectories of atlases based on age or different factors, and do a dimension, a registration on that dimension as well. Thank you.
Thank you. Now it's time for also then there's the You're there. You can just
Hello? Can you hear me? Okay, yeah, sorry, I couldn't hear very well. What was the question? Yeah, thank you, Nicolas. Congratulations on your work and on the presentation. Also, great talk. And also, I'd like to specifically congratulate you for your giant contribution to geomstats. Yeah, so of course, you restructured a big part of the library, also added a very large portion of new code. But also beyond these contributions to the code itself, I think I'd like to congratulate you for your leadership in the maintenance of the package, for example, onboarding new contributors, organizing hackathons, reviewing the code of collaborators. And all of this takes a lot of time, but also so instrumental in providing a useful tool to the community. So thank you also and congratulations for taking the additional time to do all of this. I have one question, maybe from a user's perspective, as a user of the geomstats package, for your implementation of the chilled ladders and pole ladders. But first, for the chilled ladder, about the parameter alpha, do you have a bit more intuition on how I can choose it from a user perspective, and if there are any trade-offs there? And I think just generally some intuition about the constant tau and beta that characterize the convergence.
So in fact, thank you, Nina, for the comments and for the question. In fact, the parameter is not that important. So the intuition behind the parameter is that the largest, so in fact, it uses the multilinearity of the curvature tensor R, because so W is always scaled. For example, let's take the shield ladder. W is always divided by n, and then it's remultiplied. So if it appears 1, it doesn't count. Sorry. V and V, so what counts is the number of times that V appears. If it appears once, the amount by which we scale it does not count, because it is then remultiplied by what we have scaled it by. So here in shield ladder, it appears twice, and that's why we have alpha remains once in the final result. And so the largest, the better. But then there is a term which has an order 2. So there's no point in using some alpha more greater than 2, because the convergence speed will be quadratic anyway. And if we use larger, then we might have numbers that are too small and have floating point errors because of the numbers that are too small. So I guess for shield ladder, the optimal value is really 2. And for pole ladder, we don't have a third order term. So the dominant term is the one where V appears 3 times here. Or no, where W appears, no, okay, it's this term. And here so alpha does not appear specifically, because no, it's the term where W appears only once. No, where V appears only once and W appears 3 times. Sorry. Okay, so it's this term here with W, because then so if we put alpha equals to 2, we would only have something quadratic. But if we put alpha bigger, it remains quadratic because we have W 3 times, and the term with V only once does not count. And especially when using infinitesimal schemes, if we use alpha too big, then we have stability issues. So the optimal value is between 1 and 2, depending on the dimension of the problem and how efficient the computations are and how stable they are. But it's not it does not matter as much in pole ladder. And shield ladder, it's optimal with alpha equals to 2. And then I think there was a second part to your question.
Yeah, thank you. If you could, but I think maybe it was a bit embedded in what you said when commenting on these equations. But my second question was if you could provide a bit more intuition about the tau and the beta for the convergence of the chilled ladder. Yes,
so they really come from summing these Taylor approximations, and they are the ones that are dominant. So where W appears the most and V appears only once. So tau was the one due to this one. And for the sphere, we can really, because it's symmetric, the curvature stays the same along the geodesic along which we transport. So we can really sum it and compute it explicitly. But in general, it may vary, and it comes from summing these different curvature terms. So it's really due to a bound on the curvature in the neighborhood of the geodesic that we are transported.
Excellent, thank you. And so if I understand correctly, for the chilled ladder, alpha equal 2 will be the safest default. And then if I'd like to choose between using the chilled ladder and the poles ladder, is the poles ladder always preferable?
Yes, because it's cheaper. So you don't need to compute as many geodesics when using the pole ladder because of this. Yeah. So in the shield ladder, we always have to alternate with this construction, whereas in the pole ladder, we don't need to plot this intermediate geodesic, and we can simply do a sort of zigzag like this. So there is in shield ladder there are twice as much geodesics to compute.
Great, thank you.
Thank you very much, and thank you also from my side for very nice thesis, and I also appreciate much both the scientific work and also the data part. So I have a couple of questions, and maybe I'll take the ones that relate to the better schemes first. So my first ask is, now you compare the different schemes, but you could also compare to just computing the stuff symbols and doing numerical space, I guess. So my question that would be, how would that sort of that direct way of doing that compare those in terms of accuracy and
So there are two cases. The case where the geodesics are available and in closed form, and not necessarily the parallel transport. This is the case, for example, of Kendall-shaped spaces, because the geodesics are projections of the ones of the sphere. And in this case, it's very efficient to use the pole ladder because the geodesics are easily computed. And then there is a case where we don't have the geodesics, and we have geodesic equation in both cases. And then it's a matter of how the parallel transport equation can be reformulated. For example, in a Lie group, we can reformulate it in the Lie algebra, and then it's more efficient than using ladder methods because it's just linear algebra and integration within the Lie algebra, and it's easy. It's as easy as computing geodesics, and so let's just compute parallel transport. But then then in the more general case, if we don't have a way of reformulating the parallel transport equation, but we have a way of reformulating the geodesic equation, for example, in computational anatomy. So geodesic equation with the Hamiltonian system, it's not that hard to compute, so it's a good balance between the two, and that's where ladder methods are quite useful. And in the more general case, then the geodesics and parallel transport are as complicated as the two because of the Christoffel symbols, because it's cubic in the dimension. So there are many, and I guess it's similar to use the integration of both equations, but we have to integrate the geodesic equation anyway. And so using pole ladder, it's not that much of an additional burden to have parallel transport, except that we have the logarithm, but otherwise we can compute it in one pass through the main geodesic.
And the next question is, as I understand the Taylor expansions and the convergence rates are only for finite dimension. And do you think that is there any chance of doing anything like this for
I don't know in general, because also what I used from finite dimension was, because there are two things. There's the Taylor expansion of the exponential map and the logarithm. And this, it could probably, there could be an equivalent in infinite dimension. It's a bit like the BCH formula. I think there is an equivalent in the infinite dimensional case, if I'm not mistaken. So probably in infinite dimension, we could have similar formulas. But then there's the fact that I use the fact that the curvature was bounded. and this is trickier, I think, in infinite dimension.
Yes. Yeah, and then okay, so then my next question would be related to geomstats. And so I think my question is, did you implement the manifolds where they are given by charts?
So no, we did not need them so far because we implemented manifolds for which we have a global description in all cases. So maybe in the future we will, but so far we didn't need it. And I guess I'm not sure yet. I don't have the example yet where it would be more useful. Well, if we don't have a global description, of course, but for example, with the sphere, and if we want to use spherical coordinates, we have one singular point. But then it's I don't think that we would need to exchange between charts because it would never fall on exactly on the singularity.
So maybe, yeah, if you think about doing it for manifolds that you learn the next week or so, I also just like personal experience, if you know that I do stochastics, that is, and if you run like a bounding motion on the sphere, then maybe you will not hit exactly the point around, say, for example, the North Pole of the singularity, but you will likely come close to, and then your numerics will be progressively off around that case. So that, at least in my experience, was a good example where I had to shift the chart. And then comes all kinds of interesting things about like how do we do the chart conversion and how does that affect. So one thing is the point, but if you don't have a 10 effect, cosine effect. Yeah. And I think maybe the last question is if you did any kind of taste of stochastic algorithms.
Not yet. Yeah, but we had invited your students to our hackathon, but then it didn't happen because of COVID. But it's something that we could definitely do in the future.
Maybe it will happen. If I come to you, maybe it will happen.
So thank you, Nicolas. So there are not so many questions there. But anyway, let me go back to what I didn't understand in your answers. So first, the question of the sound machine. So it was on your slide where you have this dependency lambda is equal to something to the power of beta or alpha. So to me, it's like you have a global. So you say that lambda is quite stable over the dimension?
Alpha. Alpha seems the same in dimension 2 and 3.
And so this implies it's a global function in the right? And so I think the framework that we developed in math still apply to this function. And you suggest, in fact, it boils down to a similar metric. So what you observe, and say, I would say that your proposal is what we done through this particular.
Yes, because in fact, when I tested your framework, I used the log of that function. So it's
yes, and I wanted to tell you that with the log. In fact, our motivation was to create a Riemannian metric for which global descriptors that we will do change is respected. And we think it would be possible to develop such kind of metrics, but for more complicated descriptors like area strain. So you've got a bunch of numbers of the area strain. And what you could do is to look at the the change of it in the distribution of the area strength. And will it be possible to construct, let's say, manifolds with respect change of the distribution of the area? Have you thought about
So I did measure how the area strain changed with parallel transport, but I did not try to preserve it because of the distribution across the whole ventricle. Here we only had the scatters, so it's much.
If you look at the collection of scalars, you collect
Yeah,
gives you a distribution, then you try to do something more good, or some distribution, variation in different spaces, along with local changes. You think it's possible, or maybe my question is
no, I think it does make sense if we just sum all the scatters, or we don't consider the proximity between the numbers. But I don't know whether it would be too constraining compared to the volume changes. But maybe it would maybe there would still be enough. The information would be coherent enough so that it works. I don't know, and definitely in terms of computation, it would be much harder. But maybe it could be. We could try. Yeah.
okay, so in fact, it's related to the fact that you don't know the metric and you are using data, and maybe it would be nice to learn it from data. And in particular, in the last slide we presented, you mentioned domain adaptation. And so, for instance, people in domain adaptation propose a transport. It's model-based, and in fact, it's not clear at all that transport will work for domain adaptation. And what to propose here is to use the parallel transport. The parallel transport is defined by metric, to have a sense of what is this metric. What could you propose?
What could I propose?
Yes, because in fact, what can you do? Your parallel transport, the parallel transport can be applied, but in fact, Human transport has been proposed, it has been applied, in fact, it's not better than whatever.
Yeah, but
in fact, the underlying problem is that so
yeah, well, with the advantage of the geomstats framework and the ability to compute parallel transport with any metric with ladder methods, that at least we could compare the metrics easily in the same framework. For example, I know that with EEGs, parallel transport has been proposed, in fact, but with the affine invariant metric. And I was thinking of trying with different metrics, for example, the Bure-Wasserstein one, that works better with different ranks of the matrices if they're only positive semi-definite. And so the idea would be that at least we could try different metrics more easily.
Yes, you propose geomstat as a way to explore the collection of metrics.
Yeah. Yeah, because it's modular, because we can use the same algorithm with different metrics.
And also, so I congratulate you for the numerical analysis of the parallel transport. You remember, I tell the group, we tried to implement the different experts. There was only one which was the work for me. So which was a shift ladder and pull ladder. We not have any explanation, and in particular, what was different in my implementation is that I was using landmarks, collection of landmarks. And the main difference is that I have the number of landmarks which comes in play, and when I increase the number of landmarks, the scheme, the only scheme which seems to converge was pull ladder and shift ladder. By cutting some sort of high frequency in the parallel transport. Did you observe similar problems, numerical problems, when you implemented parallel transport in the So my question is not about time discretization, it's about space discretization. When you go from infinite dimensional basis to finite discretization.
So I think I came close to what you observed when I used different frequencies to sample shapes, and I compared the ladder methods and the fanning scheme with the different frequencies. And at some point, ladder methods worked better. But then, in fact, I realized that it was due to the bandwidth of the kernel. So that if it was well adapted, then we could retrieve something that was more stable. And then the threshold that where it becomes unstable was different between ladder method and the fanning scheme. But with the right bandwidth, it worked on this example. So maybe, I don't know if you adapted the bandwidth with the frequency of the noise in the data. It's what I observed that it was important.
And there is one answer that I don't understand. Answer to Stefan's question. So, finite transform in the simple ODE. Why didn't you implement a simple ODE to benchmark the two?
So I did in some cases where it simplifies. I did not implement, well, in fact, it could be doable with geomstats.
Because if you have a machine,
Yeah.
simple, then you can compute it, right? Why did you do that? Just benchmark.
I think, yeah, because every time I did it, then there was another formulation of Fourier transport. So for example, with big groups. Yeah. Yeah, but then these schemes are they were used. So it's a good thing to understand them.
Yeah, that's question. With that, I thank you very much. I learned a bit how to get rid of this one overhead to the power platform. Thanks to the integration.
Thank you.
So thank you, Stanley. Thank you, Nicolas, for this nice presentation, and thank you for this previous work together. I will not even say that I advise you. I would say that we more worked as colleagues for research. That's how I consider the periods that we spent together. And I think I was not the only one that stressed that we had collaborations with other people outside the team and publications in journal publications of which I'm not involved, because that's just your work. So you already have actually your network of collaborators, and you're already a very, well, I would say, accomplished researcher. So I would stress that, of course, I have no questions, so I just have I should have maybe started with that. I would like to stress that you have real competencies in 3 very different domains in mathematics, as we have seen with the, for instance, the analysis of geomstats that actually closes a problem that I was trying to solve for the last 10 years. So I thank you for that. And this idea of rescaling with a different power is really something that was not at all something I would have picked up. So it's really, your work here was really instrumental. So that's for the math part. For the computer science part, well, we have seen all the work that you have done on geomstats, and Nina underlined the leadership that you have in the current animation of the development community. And I think it's going to continue, and hope so, because we're just currently recruiting a new engineer that you're supposed to advise. You will do that much better than me. And the third domain is medical application of medical imaging. And I want to stress that you already have some experience on the brain before you here. Now you have an experience with the heart. So maybe you have done the two most important organs in the body. So I wish that you will be able to deal with all ones in the future. And well, that's about what I wanted to say. Maybe the last thing is you did so many work that you could not present everything. And I find that the choices you made to present just some parts of your work are very nice, and maybe it shouldn't get noticed that it's actually not covering the full range of your work. And so thank you very much for that.
Thank you, Xavier.
Thank you. I still have one question. Just matter. I very much appreciate what you've done for developing a field, especially and all the need, as really said, and the implementation of this package. My feeling is that we might like one very compelling example where all these techniques can actually make a difference for our concrete problems. So we all work what is your feeling? Is there in this domain one day one example where you see that look, there's a lot of choice. Everything that you can try to do that as good as using well, it is meaningful to us the is this meaningful? Is this somewhere else? What is your opinion?
So I think that it is thought to be maybe not established, but is that it is accepted that it is important for the analysis of EEGs. I've heard Alexandre Confort say that Riemannian geometry has proved to perform better than Euclidean machine learning. So I think this is one of the fields in medical imaging. And then there are more traditional fields such as directional statistics. It's called differently, but it's what they've been doing for many years. And although it doesn't have the same visibility, I think it's still an interesting research domain, and that's where it could be improved by these techniques. And then more broadly, I think it remains close to the analysis of covariance or correlation matrices. Not everything has been tried, and maybe in signal processing, some applications will come up, and the difference will be clear to everyone.
Okay, thank you very much. So now is the time for a meeting of the committee closure. So I guess we are meeting this week. So the audience would